Hey everyone. Today we're going to look at day 7, independent events, and we're going to how do we determine if events are independent? So we talked about recently conditional probability, and that really conditional probability is given that something has happened, what is the probability of a different event happening? So what we're going to look at is what if one event happening does not affect another event happening? What is that called? Well, we say right here, we say two events are independent if the occurrence of one event does not change the probability that the other event will happen. So before we look at the definition of independence mathematically with probability, let's talk about just the concept of independence. So two things that are independent. Remember, think of two things that you do that one has no effect on the other. The common one I use in stats is flipping a coin and rolling a die. If you flip a coin and get heads, is that going to affect what happens on the die? No, not at all. So let's look at some more trickier examples. Are the following events independent? The first flip of a coin is heads, and then you pick up the coin again and you flip it again and it's heads. Do these two events affect each other? And this is a common misconception that people don't understand, is that independent events have no effect on each other. This is independent, right? And this is like the example, if you flip a coin 10 times in a row and you get heads. On the 11th try, people are like, oh, it has to be tails. No, not at all. The 10 events have already happened. This event, each event is independent. What about draw a king from a deck of cards without replacement and then get another king? Well, that's going to be dependent. Why? Because you get a king the first time. You might not know this, there are 4 kings out of 52, but after that, if you don't put it back, then how many kings are there? 3 out of 51, and these are not equal, right? This is dependent. So we say that two events A and B are independent if the probability of A given B equals the probability of A, and the probability of B given A equals B. And that's a lot. That's a mouthful. I like to look at it not left to right, but right to left. Let's look at it this way. The probability of event A is the same as the probability of event A given B has happened. So the probability of getting heads is the same as the probability of getting heads given that the first coin was heads. Doesn't affect each other. They're the same, right? So if an event happens, it's the same probability as given that a different event has happened. All right, so in other words, B does not affect A and A does not affect B. Okay? Now, when showing independence in a formula, there's a few ways to do this. You'll learn in stats one day. One common way is you just have to show that one of these is true. You have to show that the probability of A given B equals the probability of A and B over B. Right? Or you could also just show this, right? So let's take a look. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So there are 57 total people. There were 30 female, 27 male, and then they asked what their favorite subject was. Part A, find the probability that a student's favorite subject is math. Well, how many people chose math? 18 out of 57. Let's figure out what that is. 0.3158. Find the probability that a student's favorite subject is math given that they are female. So given that they are female, out of the 30 females, how many like math? 8. That's 8 out of 30. Let's see, 8 out of 30, 0.266666666, so 0.2667. Okay, so now think about it. This is the probability that someone liked math. This is the probability that someone's favorite subject is math, given that they're female. So are the events math is their favorite and is female independent? Well, let's take a look. Probability that someone likes math equal to the probability that someone likes math given that they're female? Are these the same? Well, 0.3158. It's the probability that anyone likes math, but if you're female, the likelihood that your favorite subject is math is only about 27%. So these are not equal, so these are dependent, right? Meaning, I can't spell this morning, sorry. What the heck? Dependent. Sorry. Right? If you're female, the likelihood that your favorite subject is math is different than just anyone liking math. Okay? Number 3. The result of a survey of the student body at Central High School about television viewing preferences are shown below. Are the events student is a male and students prefer reality series independent of each other? Well, what's the probability that a student is a male? How many males are there? 230 out of 490. What's the probability that a student prefers reality? That's 180 out of 490. All right. Now, what are we asking here? Are these two events independent of each other? Well, if you're a male, there are 230 out of 490 males and 180 out of 490 reality. So, does the probability that you're male, given you like reality, equal the probability that you're male? Right? And why am I doing this? Let's take a look again at our formula up top. We have to show, is the probability of event happening the same given that a different event has happened? So it's A given B equals A. So here, there it is. The probability of event A, it doesn't matter which one you pick either. I picked male. The probability of being male, is that the same as the probability of male given that you like reality TV? Well, let's see. What's the probability of being male? 230 out of 490. What's the probability of being male given that you like reality? Well, the probability of being male given you like reality is 70 out of 180. And now we have to check if these are the same. Hopefully you can see. Actually, one sec. 70 out of 180. 230 out of 490. And they are different. 0.38 does not equal 0.47, so dependent. All right, guys, you could try the homework tonight, and I'll talk to you guys later.